So let's make a start thinking how we can adopt microfluidics in the kind of research that we're doing ourselves. And one of the most useful parts, if you're new to the microfluidics field, is to start looking at the papers and see if you can understand how they've produced what they had. And once you go from a product to understanding how the things were made, there is a process in engineering that is called reverse engineering. And here this diagram illustrates it very nicely with an iron, where we can start off having an iron in our hands because we've used it for our clothing. We can then optically look at it and see what are the different components that it exists of. Both physically, we've got a handle and we've got a water reservoir if we also want to do some steaming. We've got a part where the cord needs to come out. But also functionally, if we want to have a steam function, it means that we need to have some kind of fluidic connectivity to allow our water to go into the heated element. Other important part, if we want to iron with high temperature, we probably need to have a heated element in there, which needs to be able to withstand high temperatures. We probably want the plate on the top of the iron to be homogeneously heated, because we don't want one area of our fabric to melt, whereas the other one isn't hot yet. So we can start thinking about how the 3D model looks like, create a mimic, and then start assigning different functionalities, and then start understanding how this iron was actually manufactured and assembled. What were the different functional units that were in the in the device, and how have they come together? A cord, with the design of a iron, you probably didn't need to make a new cord. You could just interface the electronics with an existing cord that you could source somewhere. Rest of the layout, the upsides could probably very well be made by injection molding because it's plastic. But the bottom here is metal. If you make that to plastic, it probably would melt when you were operating the machine. So if you look at any object around it, you can actually look at it and kind of start thinking, how did they make this? What were the different thinking steps? And move backwards from having a functional object in your hand to how would this have looked like on the drawing board? And if you do that with a couple of microfluidic papers this is the thing that they ended up with. What were the thinking steps? What were the reasons? What were the decisions made? And were these reasons, were they trivial? Or were they very important for the end product? Like the decision here to have a water reservoir is probably very important for the function, because you can't steam if you don't have a water reservoir. If this water reservoir is blue or pink, it's trivial, because it doesn't matter what the color is. If it's transparent, it's probably quite useful. If you're using your iron, you can actually see if there's still water in there or not. So transparent as a functionality is useful. Color, just trivial, and pick whatever the color is that suits with your brand or that you think that your consumer audience will interact with best. But if you start understanding what are the functional decisions that allowed for functionality, and what were the decisions made that were just because it was available, then you also understand, if you want to replicate that research, what are the parts that you don't want to change and what are the parts that you can actually have some flexibility. Did the people here use paper microfluidics because it was the best thing to do? Or did they use it because they had nothing else available? And should I be looking at other materials? With paper microfluidics, maybe they have used nitrocellulose instead of normal Whatman paper. If they've done so, they probably wrote somewhere in the paper why that was. Maybe it was the wicking rate, maybe it is because there's smaller pore sizes available and they wanted to have a very slow rate. If there's no information given, but they seem to have made a really odd decision, don't feel bad sending an email to the corresponding author and just see, all people doing this use Whatman paper and you use nitrocellulose. Was there a reason to? And then the answers could be, we run out of filter paper. We started a student with nitrocellulose and there we finished it. Or they may have done all the work on Whatman paper. It didn't work or it had very poor binding capacity. They then moved to nitrocellulose and everything worked beautifully. So material choice, there typically behind decisions, if there's an important story, it should be in a paper, but it is not always spelled out. But if you understand that the Whatman paper is not the same as a nitrocellulose membrane, and you know that all people that have done immune assays have used Whatman paper, and this one recent article that you found has used nitrocellulose, it may be worth asking the question, why have they changed the material compared to what the rest of the field has already done? Similarly, if people have used a laser cut fluidic structure from tape or an injection molded device in PMMA, the reason for picking one or the other may very well the availability in the lab. It is very easy to get a xerography machine and cut some double-sided tape to size as spacers. Whereas injection molding equipment, it's expensive equipment and it needs a sophisticated operator to run it. So not every university has got access to an injection molder. Commercial devices are quite expensive. Xerography using double-sided tape is really cheap. So the decision there may not have been made on the materials because they may use PMMA still as a top and a backing. The decision there was made, I can quickly prototype and get my student through for very little money if we use a laser cutter. If we ever want to upscale, we can think about injection molding, but at this stage, not yet. So understanding in a paper what has been used and trying to understand why certain decisions were made. There are some like-for-like decisions, and you can easily swap if you don't have a xerographer machine, so you can't cut, but you've got a friend in the engineering department that's got an injection molder. Maybe actually you can do a very similar experiment using your engineering friend's injection molder. Doesn't change the device and the geometry at all. Hi. And it is make the microfabrication do whatever you want to do. So if you analyze a paper in the literature, ask yourself the question, what was actually done? What was new? What was effective that was done? Do they argue how it was optimized, why it was effective? What does the author themselves say about what the novelty was and what the reason was that they did it? Because typically it's hidden somewhere in the discussion of the results. We use PMMA because PDMS is a solvent and our analyte disappeared. Then you know that if you look for that paper for the same analyte, perhaps PDMS is not the one to go. Whereas if they just say they worked with PDMS and there was no problem and the analytical results look consistent, then probably the analyte that they worked with was not very hydrophobic and the absorption of the analyte into PDMS was not a problem. At that point you can make the decision, do I want to stick with PDMS, have a risk that there's absorption, but have soft lithography as a very fast and effective microfabrication method? Or do I want to look to see if I can get another microfabrication approach to work with a less sorptive material to not even have the risk that my analyte will be disappearing? The other thing to ask is, we have solved a couple of different issues here, but we may not have addressed all here. What are the issues that are still remaining? What are the challenges that the authors may have mentioned? Or what are the difficulties that I can see that the authors haven't mentioned at all? And does that provide me with an opportunity to do a new research project or to do it slightly differently? Every paper has got a different scope. Sometimes it's an assay that has been developed for a target that has never been used before. Sometimes a new functional module has been developed, a new type of light scattering detector. Use of a multicolor LED to do multicolor fluorescence detection. Sometimes it's technology, which could be in the manufacturing, introducing the use of 3D printing for making these type of devices. Sometimes in the technology in the fluidic dynamics, introducing a new type of mixer to get better, smaller, more monodispersed nanoparticles being formed. Sometimes it is in putting everything together into a full system. Sometimes different individual components have been developed, either by the same research group or by different research groups, and someone is putting it all together into a single box. As we've seen yesterday, the development of a sample in-answer out system that does sample preparation, sample pre-concentration, the assay and the detection, doing that all in a single integrated platform in a single way is not an easy thing to do. So maybe the novelty of the paper is having sample preparation or sampling, sample preparation, assay and detection, having it all happening in one box, because for this analyze, and or this matrix, that hasn't been done before. Maybe it's a miniaturized total analysis system that's got an automated sampling system that can allow for it to last any longer. So it is important to understand what the problem is that the paper addresses, and to understand if it's got an application-based focus or technology focus, because you can't really win on both sides at a time, because that would be like doing an experiment where you change the 2 parameters at a time and you can never figure out why it worked or most often didn't work, because you haven't isolated a single parameter, so you can't draw any conclusions on a single parameter. So papers will always have either a focus on the technology development, on the assay, or on the application. So it is important to start visualizing the detail. What does the device look like? How does it work? What happens if my sample comes in? How are reagents added? How are the different fluids manipulated? How was it made? Was it made by casting? Was it made by a replication technique? Was it made by 3D printing? And also get an idea of what the additional infrastructure is, because particularly if you want to repeat a particular experiment in your own lab. If it's using HPLC pumps, they require really high pressure. So if they use the HPLC pump, maybe this system is not going to be very effective if you don't have any pumps and you're relying on gravity feed or maybe a peristaltic pump. So every different pump that is available on the market has got a different flow rate range and pressure range. You need to understand that you can't, without any issues, swap one pump over from another. Because a pneumatic pump has got a really smooth flow profile coming out, because it's the pressure that just dictates the flow at a certain constant rate. Whereas if you've got a peristaltic pump, we've got these rollers. So we've got a little bit of water being pushed forward over and over again. So we will have a pulsed flow. Biological systems quite like that. So there's actually, in cell culture systems, there's no problem having pulsative flows, because our heart is a peristaltic pump. But if you talk about the chromatographic separation, maybe your efficiency will suffer if you try to do HPLC with a peristaltic pump. You won't be able to generate the back pressure, but even in an open tubular system, the pulsing will deteriorate your separation. So again, the fluid mechanics are determined by the fluid control and the pumping system that you take. So understanding what pump they used and why, and quite typically it will be explained somehow a little bit in the experimental, is important. Was it important to do imaging? Do they show any imaging? Did they need a confocal system? Or would just be a USB microscope enough to do this? So what is the setup in the lab that you need in order to repeat the experiment that you would like to repeat in your laboratory? And it's always worth to just, were there alternatives? Would they have been equal, better, worse? And yeah, glass is better to do some organic synthesis, but it's also harder to make. So even though there is a better alternative, maybe there's other reasons like safety in the lab or cost that still led to the decision to work in a polymer device. Other questions to ask is, would I have done the same? If I would have that problem and I needed a microfluidic solution, would I have done the same? Could I do this? Could I do this differently? Could I do this better? And then by coming up with some of these answers, you may start formulating the way you're going to conduct that instrument in your environment where you are, with your collaborative network that you've got around, with the skills and the instrumentation that your supervisor already's got. So the big day tomorrow will be examination. And I selected 4 different papers. Professor Malik printed 2, so maybe we'll just do it on the 2 papers. And I picked them to be relevant to either nanoparticle synthesis or to agriculture. So we've got one paper that looks at a very fast mixer coupled with a very funky bit of detection electronics to study ultra-fast reaction kinetics. We've got an agricultural example here where there's paper microfluidic devices for the assessment of durian fruit ripeness. We've got a 3D vortex here for making core shell particles, and we've got the green synthesis of pepsin-doped gold nanoparticles. The ones that I've got available to look at here for you now are the durian fruits and the green synthesis of the pepsin-doped nanoparticles. So what I would like you...
Green synthesis?
The green synthesis I've got here as a printout and the durian. So the bottom left and the top right corner. Otherwise I can send you the PDF if you want to have a look at any of the other papers.
You can share.
But we've got the printouts here available. And what I'd like to do tomorrow with you, and you can come in groups, you can come individually, I don't really care, is to just have an informal conversation on seeing by reading those papers if you can answer what the material was used to make the microfluidic device. What is the microfabrication approach that was followed? Was it soft lithography? Was it made in a clean room? Was it made by simply stacking some bits of plastic together? What microfluidic phenomena were used? Is it laminar flow? Was there a mixing element? Did they play around and did they use the high surface volume to surface to volume ratio? Did they use wicking? So what of the microfluidic phenomena that we talked about in the first week did you actually see come back in this paper? And I'd like to know what you like best about the paper, and that is a question. Unless you don't answer it, you can't have it wrong. What is the kind of features in this paper that you really thought, that's clever, or I'd like to do that. So I'm not going to assess you on if you can repeat the Reynolds number. I'm not going to assess you on any of the physics. My goal here was to make you think how you in your type of research may be able to open the microfluidic toolbox and progress your own work. So if you've seen another microfluidic paper that's really close to what you do, I'm quite happy for you to bring that tomorrow as well. Don't get nervous. We don't need to have a 2-hour conversation because we only have an hour for all the interviews. I just want to have a quick chat to you to see if you could understand the paper, what you got out, because that also gives me a little bit of an insight how much of the information that I've tried to send to you, how much you actually received. And that then allows me to do better again next time. So feel free to pick one of the papers here, and if we need any others, I'm happy to share the PDFs.
The copies?
So these are photocopies of the 2 papers. I don't know where the other 2 are. Maybe they didn't end up in Professor Malik's inbox. But I've got all the 4 PDFs here, so I can just email individually so you can read to them on the screen. But I thought they would be kind of relevant here to the audience.
Yeah.
Are we finished with the topic?
Yeah, I'm finished with the talking. We now just do the assessment. Yeah.
And we can stop.
We can stop. Yeah.
Ma'am, we have to read all the 4 papers or any?
On one.
Okay.
And if you find another very brief communication